Okay, thank you. So welcome back to part 2. Right, so let's just do a quick recap. Right, so we are trying to prove theorem 10.1 and we have reached this point. We took a maximal unstable barrier and that includes a DM barrier, so we get DM barrier anyways. And then we concluded that the ends of F actually lie in distinct odd components of G minus F minus B. So all that is fine. The only thing that remains is the second property, which is significantly harder to argue. Not too difficult, but anyways, we'll see. So we want to show that for every odd component of G minus F minus B, it is a shore of a separating cut. Okay. So that means if I pick one odd component, K, if I pick a particular odd component K, which could be this or this, doesn't matter. We want to show that both the contractions are matching covered. The easier contraction is the one where you shrink the complement. Okay? So if you shrink the complement of the vertex set of K, then to show that it is matching covered is actually not too difficult. Let's do that first. So what we'll first do is, for each odd component K of G minus F minus B, if I shrink the complement G shrink vertex set of K complement to, I don't know, little k bar, is matching covered. In fact, we'll show something stronger. We'll show that it is actually bicritical. Yeah? See if you can do this. For every odd component of G minus F minus B, in fact, if I'm not mistaken, this argument should go through for B star as well. This one is not the problem. The problem is going to be the other contraction. See if you can prove this. For every odd component of G minus F minus B star, so even the odd components on this side, but we don't really care about these ones, we care about these ones. Okay? See if you can prove that when you shrink the complement to a single vertex, the graph is bicritical. Yeah, DIY. Right, let's make one drawing. I'll draw for this fellow. So K remains as it is, and everything outside becomes a single vertex, little k bar. See if you can prove this. So I'll give you a hint, which is the hint I've given many times for many other things. Here is the hint. G is a matchable graph. G minus X minus Y is not matchable if and only if there exists a barrier containing both X and Y. This is probably one of the most important statements in all of matching theory. Pretty much any paper I write has this statement because we need it for life. So see if you can use this. Right? Don't throw away the theory. The theory has lots of tidbits that are very crucial. So which assignment? Okay. Apparently it looks like this also follows, whatever we are trying to do, it seems to also follow from some assignment problem. Okay, so try this, right? This is the point. So what is clear is that you want to show this graph is bicritical. If you delete the shrunken vertex k bar and any other vertex, then of course it is clear, because we know that the odd components are critical. So if you delete k bar and some other vertex, then the remaining graph is matchable, right? So maybe let me call this k prime. Did I give it a name? Yeah, this fellow. I'm calling this graph for now k prime. What is clear is that k prime minus little k bar minus some other vertex x is matchable. Yeah? For all x. This is clear? Now we are going to apply this. But before we apply, we should make sure that the graph is matchable. This also proves that the graph is matchable. Take a neighbor, take x to be a neighbor, and now observe that if I delete these two vertices, there is a perfect matching, include this edge, perfect matching of the whole graph. Therefore, this graph is matchable. Yeah? So the only thing that remains is to show that for any two arbitrary vertices coming from this part, g minus x minus y, k prime minus x minus y is matchable. Well, if it is not matchable, then inside k prime there is a barrier containing both x and y. This barrier cannot contain k bar by the same proposition and the fact that this graph is matchable. If there is a barrier containing x and y, that barrier cannot contain this fellow. The shrunken vertex has to be in one of the odd components or the even components, I don't care. But then actually it's nice, because then I can unshrink it, go back to the original graph, and I have a barrier in the original graph containing x and y. Therefore I have a non-trivial barrier in the original graph, contradiction to bicriticality of the original graph. Yeah? Yeah? Everybody agrees? So therefore, sorry?
Contradiction to maximality if you consider this.
Not quite. No, I just got some barrier here, which is a barrier in the original graph. That I just got some non-trivial barrier here, including x and y, and that same fellow is a barrier here. There is no contradiction to the maximality of B star. At least I don't see it right away. But yeah, there might be another way to do it. Yeah. But anyways, we don't need that. We can just say here at this point that we have a contradiction to the fact that G is bicritical. Right? So therefore, we are also able to show that k prime minus x minus y is matchable for all xy and therefore putting the first and third together, the graph is actually bicritical. Yeah. So this fellow is bicritical, therefore it is matching covered, which is actually what we need. And in fact, I don't think we use the fact anywhere that this is an odd component on the left side. We could have also taken odd component of G minus F minus B star, and everything will go through. So actually, this statement actually works for all odd components of G minus F minus B star. Right? Yeah, I think that's what I wrote here. Yeah? So this one is fine. The problem, as we saw in the earlier example also, is not actually this contraction. The problem is the other contraction. When you shrink the odd component to a single vertex. That's where the earlier example also failed, if you recall. The 10 vertex example from Lucchesi Murthy. Okay? That failed because we shrunk the odd component, we shrunk one of the triangles into single vertex, and then we had an edge that was not matchable. Right? Okay. Okay, so now we need to show that part. So maybe I'll just erase this, I need some space. So this graph is matchable, that's fine, okay. Let me erase this. K prime is bicritical and thus matching covered for every odd component. In fact, for any odd component of G minus F minus B star. Yeah? So far so good? But now we need to show that for the odd components that are drawn on the left side, the odd components of G minus F minus B, for them we need to show that the other contraction is also matching covered. So if I shrink this fellow into single vertex, I still have a matching covered graph. What we will actually do is we will do something slightly different. Instead of shrinking one at a time, I will shrink all of them into single vertices. Yeah, I will shrink all of these three odd components into single vertices, and we will argue that that graph is matching covered.
So are we considering the other odd component?
No, not these, only these.
No, in the contraction.
Yeah, what we'll do is we'll consider the graph obtained by shrinking this into single vertex, this into single vertex, and this into single
So
vertex.
which graph we want to be matching covered?
Okay. So what we want is for each odd component, we want both contractions to be matching covered.
Both means.
So yeah, that means one is this fellow, and the other is that I shrink just this into single vertex.
With the B star.
The whole graph G in the yeah. So what we really want is okay. So what remains is, let's just write down. What remains is the following: for each odd component K of G minus F minus B, the graph G, where I shrink K to single vertex, is matching covered. This is the only thing that remains to be proved. You all agree? For every odd component of G minus F minus B, if I shrink the component itself to a single vertex, I want to argue that the graph is matching covered. Yeah? What we will do first is we will consider the graph obtained by shrinking each odd component into single vertex. Okay, I'll make a drawing of that graph. This is the graph L. Okay, and instead of defining it, I will just draw it similar to this. So I keep everything as it is. This is my B star. In my drawing, this is the B part. And I will keep all of this as it is, no changes. But here, I will shrink each odd component to single vertex. And the edge F is there because I did not remove any edges. And the other edges, they look as they looked before. This is the graph L. Okay? So instead of shrinking one odd component, I have shrunken all odd components, each of them into a single vertex in the original graph G. This is my graph L. Okay? Obtained from G by shrinking each odd component of G minus F minus B into a single vertex. So if I have 3 components, I get 3 vertices. Yeah? This is the graph L. We will argue that this fellow is matching covered. And then we will argue this. Before we do this, let's see why we are done actually. Right? So the goal is the plan is to argue that L is matching covered. And I claim that if we argue this, then we are done with this. Using other facts you already know. Let's first address that before we move further. Okay? See if you can convince yourself that this suffices to prove this. So observe that basically from L I can go to this graph for any odd component. Fix this as a favorite odd component, right? So what is this graph? I shrink this odd component to single vertex, but the other odd components are as they are. My claim is that I can go from L to that graph where I have shrunken this fellow by simply splicing the other two vertices with the corresponding K prime. K primes are matching covered. We already showed that. They are bicritical actually. In particular, they are matching covered. So I am just going from L, which is matching covered, splicing with a K prime and another K prime for the corresponding component. Then I can go to the graph I want. Splicing of two matching covered graphs is a matching covered graph. Right? So therefore, it suffices to argue that this fellow is matching covered. Yeah, this is what we will do. In the rest of this lecture, we just need to prove that this L fellow is matching covered. Yeah? Okay. Questions, concerns? L is matching covered. This is what we need to do. In fact, if you go back to that 10 vertex example, in that 10 vertex example, we had only one non-trivial component, and when we shrunk it, it was a triangle. When we shrunk it, we got a graph that is not matching covered. That was actually L, because all the other components are trivial. So in fact, in that example that we had, L was not matching covered. But that is because, of course, it is not the same L. Because that is because we took all the odd components of G minus F minus B star and we shrunk all of them into single vertices. 3 of them were already trivial, one was a triangle, we shrunk it, and we got this graph where all of these are single vertices. That is actually not matching covered. That is what that example demonstrates. But if you shrink only these fellows, then it's matching covered. So what this demonstrates is that somewhere we need to use the Dulmage-Mendelssohn-ness that is going on here. Right? Otherwise you are not going to get this. Okay. So if I want to show that this graph L is matching covered, so I'll take any edge in this graph and I will take a perfect matching in the original graph containing that edge. Right? That's basically what we will do. Right? What else will we do like this? Right? So we'll take the edge in L and we will go to the original graph. We'll take a perfect matching containing that edge. The good thing would be if that perfect matching containing your desired edge, if it meets all these cuts in exactly one edge, then you are done. Then you just take the restriction and you are done. The problem is, what if the perfect matching you take here intersects one of these cuts in 3 or more edges? Then you need to do something. Then you can't just take the restriction and say that it is a perfect matching. Right? It won't be a perfect matching. Okay? So that's the main point. If for every edge in this graph, we are able to show that the same edge in the original graph participates in a perfect matching that meets all of these cuts in one edge, then we would be done. Then that edge, tick mark, it's matchable. Yeah? Okay? So this is the main idea. So let's consider some edge and we'll do some cases, right? Yeah, not too many cases, just do something. So let's consider some edge in this graph. And let's for now not worry about F. Okay, let's not worry about F. So consider some edge E, maybe not E also, whatever, D. D is some edge of L that is not F. Okay, we'll worry about F later. I would like to convince you that there is a perfect matching in the original graph that contains D and that meets all of these cuts in exactly one edge. If we can do that, we are done. Okay. We'll find something useful. We will find two cuts useful. One is this cut C, and another thing we will find useful is the edges that have both ends in B. Okay, we will call that EB. EB is those edges that have both ends in B. Okay, fine. Alright, so I'm taking an edge in L. L is this graph, and the edge is not equal to F, some other edge. So in the original graph, there is a perfect matching M. Containing this edge. I don't know where this edge is, okay? This edge could be anywhere. But it is an edge of this graph. Okay? So it cannot be inside one of the odd components because those edges have disappeared when I shrunk. Okay? So I took an edge here, not F, and I am taking a perfect matching of the original graph containing that edge. You'll consider two cases. Either M uses edges from this set, M intersection EB union C. Either it uses edges that are contained in the barrier B or that are going in this cut C. This is an even cut. Note that C, unlike most cases in life, well, you have seen even cuts before. In this particular case, C happens to be an even cut. Right? Even number of vertices on left side, because you have k vertices and k odd components, that adds up to even number of vertices. Right? So either this perfect matching meets this cut in nothing, or it meets it in some number of edges, which has to be an even number. Okay? We'll consider these two cases.
Why is it still even when we add EB to?
Sorry? Sorry. Sorry. Yeah, my bad. Sorry. Yeah, this is not true. Either it is empty or not empty. That's the trivial statement I wanted to make, but then I make it incorrect. Yeah, so either this is empty or it is not empty. That's clear. Can you all think about these cases, whichever case you like, and see if in any case you can finish? Is there any case amongst these that can be finished easily? I'll just try to tell you again what we are trying to do here. We took an edge in L that is not F. For convenience, let's forget F for now. Okay? We'll try to first show that every other edge is matchable. Don't worry about F. Now, what we will do is we will do the obvious thing. We'll take a perfect matching of the original graph G that contains this edge. Okay? And the idea would be to somehow show that either the restriction itself works. If the restriction doesn't work, then I can do something else and make it work. Okay? So, we'll consider two cases. Either the perfect matching M meets this set or it doesn't meet this set. Think about it. Make some drawings and see in which case are you done. And if you are not done, then how do you get done from there?
maximums this type of other reference and also we took the technology and G where these were called bicritical. Then we something pressure cone is also perfectly directed in this help.
Okay, so my suggestion is first you consider this case. Consider the case where the perfect matching M, right? This is a perfect matching of G containing D. We know it exists because G is matching covered, right? So we took a perfect matching of G containing D. Consider this case, right? It's possible that it doesn't use any edge. EB, just to remind you, is a set of edges that have both ends in B. That's the definition of EB. So both ends are here. It may be empty or it may be non-empty, I don't know. And C is the set of edges going from the left side to the right side. That may also be empty because B could be equal to B star, right? So, right. But don't worry about the case where they're empty. Just consider this to be empty. Assume this to be empty. The perfect matching doesn't use anything from these two sets, EB or C. In that case, what does the perfect matching look like? Right? You all agree in that case, the perfect matching, basically the perfect matching M meets each of these cuts in exactly one edge. Is that correct? Are you all convinced? But if it meets each of these cuts in one edge, then I will just take the restriction here and I have a perfect matching containing the edge D of this graph. So I'm happy. You all agree? So therefore in this case we are just done. The case where we are not done is this case. Yeah. Okay? Restriction of M to the edge set of L is a perfect matching of L containing the edge D. Yeah? Everybody agrees with this? Yeah? Now let's suppose that the intersection is non-empty. Yeah. Then what does it look like? I need some more space, so I'll make some more space here. Now suppose that your perfect matching M actually meets this set EB union C. Then what does it look like? Can you make some drawings and see what it looks like?
vertices match outside or within, the remaining will be at red.
I hope you're not assuming these are triplets.
I'm not assuming these are triplets. Oh, I think I'm forgetting the existence of it.
Let's make some drawings. So yeah. So let me see. So I'll make one more drawing of this situation. Maybe not. Okay, so we are considering some perfect matching in this graph, and we are trying to understand what is the intersection with this set, right? So if it is empty, then we already finished that case. Let's consider the intersection is non-empty, right? So either there is an edge in EB that we are using in this perfect matching. So let's consider that case. Supposing there is some edge here, E, that is being used in this perfect matching. Yeah. So then, okay, yeah. The point is, I have three odd components. There are no edges going from these odd components to those vertices in B minus B star. This is B star, sorry, B star minus B. This is B star minus B. There are no edges going from here to here. There are three odd components. Two of the fellows have already been matched. Well, we are in trouble unless we use the edge F. We must use the edge F. If I use an edge from EB, I must use the edge F. The remaining odd component, or as many as possible, they go to the remaining vertices here. Of course, I drew only 1 and 1. It could be K and K, doesn't matter. Yeah. They have to go to these fellows because there are no edges from them to this part. Yeah. So this is what it looks like. And of course, what about the rest of the perfect matching? Well, now observe that, let's see, since there are no edges from here to here, the rest of the perfect matching on this side has to look like this. You all agree? There are no edges from here to here. Therefore, I must match the other vertices here itself. What do you see in this case? The intersection with all the cuts we are interested in is equal to 1. In these cases, in this case, the intersection with all the cuts we care about is 1. Therefore, if I take the restriction, I'm done. Yeah. Okay, let's make one more drawing. Okay. So what happened in this case is we considered that the perfect matching M is using an edge from EB. We assumed that M intersection EB is not empty. Yeah. And actually we were able to conclude in this case that M intersection C is in fact empty. Is that correct? Yeah. And we were able to more importantly assume that M intersection partial of K, I don't care about these components, I care about these components, is equal to 1 for all odd components K of G minus F minus B. And this is very happy news, right? This is exactly the kind of stuff we are looking for in life. Okay, now let's go to the other case where I'm going to assume that M intersection C is not empty. Right? If the intersection with EB union C is not empty, then either the intersection with EB should be not empty or with C should be not empty. At least one of them. Well, C is an even cut, therefore we must use at least 2 edges. Well, the edges of C, we know they don't go from here to there, they go from here to here. Therefore, we must use 2 edges like that. So one of these goes like this, one of these goes like this. I'm not going to care about the rest. I don't care about the right hand side. I care about the left hand side. Yeah. Now I have 3 fellows here, but only 1 fellow here. And there are no edges going from here to there. Therefore, once again I must use the edge F. Okay, F was here and I must use it. And this fellow goes like this. Yeah. And now, since there are no edges from here to here, the rest of the perfect matching looks like this. Yeah. Once again, the restriction with every odd component of G minus F minus B is 1. Yeah. Is that correct? So we are done in this case. So again we are able to prove that M intersection EB in this case is actually empty, and we are able to also prove the important point, which is this point. Yeah. So in these cases we are done. I actually want to make a drawing of the earlier case again. I think we might have rushed through this. Let's do this case when the intersection is empty. I'm not convinced we did everything correctly there. Let's check. When the intersection is empty, what happens? I want to keep this. Let me just use this, right? this drawing is not being used for anything now. Supposing the intersection is empty. Let me erase a few things, too much noise. Okay, F is fine, B, E, B, all that is fine. I don't need all this is fine. Yeah. Okay. Okay. This is B star minus B. I'm going to now go back to this case, which I think we hurried through. Let's not hurry through things. Let's do the empty intersection case. Yeah, what does that look like? In the case of empty intersection, so I'm not using any edges here. I'm not using any edges in the cut. Okay. Either the edge F is used or the edge F is not used. If F is not used, then this is a barrier. B star is a barrier in G minus F. If you have a barrier in the matchable graph, perfect matching has to meet every odd component's cut in exactly one edge, right? So that case is easy. If F is not used, it is actually easy. I want to look at the case where F is used, because I think that we might have rushed through. It could happen that the intersection is actually empty. Yeah, this is possible. M intersection EB union C is empty and F is used in my perfect matching M. I think this might happen. Let's see. I can use F. I'm trying to use F. Now, for this odd component, of course, it has to match to somebody. So I can match it here. This has an even number of vertices. What could happen is possible? And complete it on the other side. The other side I don't really care about. I mainly care about this side. I cannot just take the restriction. The restriction is not a perfect matching. In this case, I cannot just take the restriction. Yeah. So if my perfect matching containing D looks like this, I'm in trouble. In all other cases, we are not in trouble. Convince yourself that in every other case, we can simply take the restriction and we have a perfect matching in the graph L containing the edge D. Yeah? D is the edge we chose, which we are not really using anywhere. Right? This is there implicit. Yeah. Right, so the only problem is this case. Let's see. Okay, so this is the case we need to fix. And where is the edge D in this figure? D could be an edge here. D could be some edge on the right hand side, right? D could be on the right hand side. Or D could be one of the edges in my matching because I took a perfect matching containing D. These are the 4 possibilities for D. Either D is one of the pink edges I've drawn because D is in my perfect matching, but I've only drawn the pink edges on the left hand side. I have not drawn them on the right hand side. D could also be an edge on the right hand side. Yeah. Now we will use the fact that this is a Dulmage-Mendelssohn barrier. This B fellow is not some arbitrary barrier, it is a Dulmage-Mendelssohn barrier. So, if D is one of these edges, I cannot just take the restriction and say, hey, I'm going home, because that is not a perfect matching, right? So, if D is one of these edges on the left hand side, what I will do is, I will keep the perfect matching on the right hand side as it is. That is a perfect matching, yeah? Because the intersection of the cut is empty. That means the restriction on the left is a perfect matching of the left, the restriction on the right is a perfect matching of the right. So I'll keep this fellow as it is. And I will play around here. I will go to the bipartite core and I will take a perfect matching containing my D. And then because these are factor critical, I will extend that perfect matching to all these components. So whatever the D is, I can keep the right hand side as it is and flip this around and get a perfect matching containing my favorite edge D and union them and have a perfect matching containing D whose restriction is a perfect matching of L containing D, right? And D is on the right hand side, then I will just take any perfect matching here. Again, I can use the fact that Dulmage-Mendelssohn, I'm just using bipartite matchable graph, right? I'll take any perfect matching here in the bipartite graph in the core and extend it to perfect matching using the hypomatchability of these components. So therefore, for all D's we are done. No, you're not convinced?
D could be F.
D could be F, but D was not F.
Okay.
But your point is we need to address F. Good. We need to address F. Okay. So now address F, DIY. Yeah? D for DIY. How do you address F? Yeah?
In both the cases, there exists a perfect matching that contains F and D.
Right. Yes. So we need to show that. So that's Anjali's point is that in these cases we actually got a perfect matching containing F. Right? And it is actually good because intersection is 1. Right? So if we can only show that these cases actually must happen, then we are done. If we can only show that one of these 2 cases must happen, then we are done. What does that mean? Huh?
We take the edge from B to the odd component of yeah, we take an edge that crosses
Like this?
there's an edge in C.
So now there are 2 points. C could be empty. At some point I mentioned that EB could be empty, and I mentioned also at some point that C could be empty. Can both be empty? Both cannot be empty. EB and C both cannot be empty. C could be empty means that this whole graph is not there. We are only looking at this part. But now there should be an edge here because otherwise F is not in any perfect matching. Therefore, EB union C is non-empty. Therefore, one of these cases will occur and we are done as per your point. Observe that EB union C is not empty. Yeah. So what have we done? We took an edge in L different from F, and we showed that in all cases, including this nasty case, we are able to get a perfect matching of of G containing the edge D that meets all of these cuts in exactly one edge. Its restriction is the desired perfect matching of L containing D. And now the only edge that remains is F, but that is the point where EB union C is non-empty comes into the picture. This set is always non-empty, and therefore you will have a perfect matching that looks like this or like this. It contains F, its restriction is your perfect matching of L containing F. Therefore every edge in L is matching covered, and as we noticed earlier, if we just splice these bicritical graphs, K primes, then we will get whichever graph we want. Right? We wanted to argue that these graphs are matching covered. Well, just splice L with the bicritical graphs you want to get the corresponding graph. Therefore, for every odd component, we showed that if you shrink the complement, the graph is matching covered, and if you shrink the odd component, the graph is matching covered. Therefore, for each odd component of G minus F minus B, the corresponding cut is a separating cut. And that completes the proof. And this is what we used yesterday to get very nice drawings in the case of solid bricks, when we had two adjacent non-removable edges. Yeah. Okay. Questions, concerns, anything that was not clear, anything that needs repetition? Yeah, all good?
So like that being non-empty, that probably does not follow from the fact that F should be matchable.
Let's see. If EB, so if C is non-empty, then what does it mean for the cut to be non-empty? It means that there is no graph here. The whole graph is here. And now if EB is non-empty, if EB is empty, then F is not matchable, right? In G.
Can be matchable.
Like we are doing in L, right?
Something like
Give me a
this,
second.
the pink stuff that we have on the right.
One second. Maybe I'm missing something.
We have an example, right?
Oh, I see. Yes.
That's an example, right?
Yeah.
Both are empty.
Yeah, so give me a second. Yeah, so good. I think the contradiction is F is non-removable. If this set is empty, wait a second, I'm confused. There are no edges here.
Yeah, follows from the unstable value.
Wait. One second. Right. Yes. You're right. Yeah. Yes. It follows. In fact, this is a very important point, because if this cut is empty, that means there is no graph here. B is equal to B star, but we know that B star is an unstable barrier, and that is crucial because in the Murthy graph there is a stable barrier that actually does not satisfy this theorem. So yes, you're right. Thank you. Good. Yeah, it follows from the fact that we took an unstable barrier. So if B is equal to B star, then B better be unstable. So AB has to be non-empty. Yeah, thank you. Yeah, good. Yeah, is that point clear? Yeah? B star is unstable. So if C is empty, then it means that B is equal to B star and B is also unstable. So therefore EB cannot be empty in that case. Yeah. One of them can be empty. Either C or EB can be empty. Both can't be empty. No? Not convinced?
But then also matchable thing goes now. Like you said that suppose C is empty
Okay.
and EB is also empty, then how F is matchable?
No, the point was to show that.
With a non-removable edge.
Sorry, can you
F
repeat?
is non-removable.
F is non-removable. That's
So
right.
that, and we are saying that if C is empty,
Yes.
then you are saying that there should be an edge in the barrier.
Yes,
because
EB.
that barrier is same.
Yes.
So that, and we started with unstable, or to match F we need an edge there.
No, we don't need. That is the point Amit was saying, that to match F we actually don't need. We could have something like this. This is a perfect matching containing F that actually does not use anything from EB. Right? So that was, yeah. I was thinking that we need this edge for F to be matchable, but that's actually not true. Right? The reason we have this edge is because we chose B star to be unstable, and now B is equal to B star. That's it. Yeah. Good. Yes.
So it is like another tricky point
Mm.
is that in the middle code
Huh.
where we chose the edge D in pink on
Yes.
the pink side, D could also be an edge in the component. Then it will
No. D in these components? No.
Ooh.
D is an edge of L, that is not F. In particular, it can't be an edge in any of these odd components because they have been shrunken.
Yeah, fair enough.
So it's not this. Yeah. Therefore, I said D is either these or it is on the right hand side. Yeah. Good. Thank you. Yeah, no, there are lots of subtle points here. In fact, so I'll tell you how Lucchesi Murthy actually do it. They have a lemma in chapter 9. I believe it is 9.12. It is one of the only things that I skipped in chapter 9. It's a very technical lemma, which is basically a counting argument. And they just apply that counting argument here and finish everything very quickly. I haven't really become friends with that lemma yet. So, if you want to see, let me just check. 8.12, sorry. In chapter 8, there is lemma 8.12, which is what they use. It's just an inequality. In fact, if you, now that we are here, let me just write down that inequality. This is the inequality they use from lemma 8.12. Two times, I use my notation, M was the perfect matching, 2 times M intersection EB plus M intersection C is less than equal to 2 times M intersection the set containing F, which just means either it is 1 or 0 depending on whether F is there or not. This is the inequality they use to conclude everything we concluded. It's like super condensed and everything just goes through. But I have not yet graduated to that level. Yeah, and in fact, when we were in chapter 8, there was a point where I could have used this inequality, but I did not do it there, and now I'm not doing it here either. But since you mentioned, there is a way to actually conclude things much faster, and this is the way to do it. But yeah, if you become friends, let me know.
Basically, this C
Yes.
size is 2
Uh-huh.
or 1 EB.
Right.
EB has 1 edge or
Either we are using one edge from EB,
or C can be exactly 2.
or we are using only 2 from this part, and then this will contribute 0.
So,
Yeah.
so it will.
And it depends on whether F is being used or not. So it actually captures everything we discussed. Yeah. But yeah, I am not able to teach using this lemma. That's the thing I'm facing. Like, I can parse it like a computer would, or as they call it, AI or something, but I'm not really friends with it. Okay. Alright. So are you all happy with the theorem proof? Everybody convinced that the proof goes through? Yeah. So okay, so what we have done so far, I'll just quickly walk you through what is happening in the chapter afterwards. So there is a very important lemma called the lemma on wheels, which I am not going to cover today. Yeah, it's somehow related to Santosh's work on V matchings. Yeah, you might want to check it out. So there is a section called the lemma on wheels. I'm planning to cover this once I come back. And then there is another whole section on implications of being solid. And one of the things they prove is that in a solid brick, every removable edge is B invariant. In fact, this is true for all solid matching covered graphs. Every removable edge is B invariant. This is one way to see why solid matching covered graphs are a generalization of bipartite matching covered graphs. Because in bipartite matching covered graphs, removable edges of course B invariant, which is also true for solid graphs. And then there are a bunch of other results which I'm hoping to cover once I come back from Gujarat and eventually we resume classes at some point. Yeah. And once we finish this, And then we go to the last few chapters about ear decompositions and conformal minors, which is related to some of the work Rahul and Santosh are doing in particular. Yeah. Okay, so anyways, we will resume afterwards at some point, and we will meet directly on 4th of May for Amit and Santosh's very nice presentation on exponentially many perfect matchings in cubic graphs. And if they are okay, we can also record it, but that's okay, we don't need to. Anyways, any questions or concerns before we conclude? Okay, thank you. And officially the last lecture of this class, but not really. Wink, wink. Okay, thank you.